Actually, what is the thing called time? Have you ever sensed the time? Have you ever touched the time? Can you feel the time? Can you see the time? And can you smell the time? The answer is no. But all of us are being controlled and manipulated by the time. So what is this extraordinary thing called time? If we can control the time, can't we age slowly, or can we travel across the time? So today I am going to talk about one of the most fascinating Einstein physics theory, that is called time dilation. Not only that, we will talk about the way of slow aging with respect to that theory, which is called time dilation. Some can say that time is inside a watch or a clock. Is that right? No, that is not right. Watch or clock is only a device we have prepared to measure the time. So when we talk about the time, we can't forget the genius scientist Albert Einstein. The Albert Einstein has done a number of remarkable research regarding this topic, which is called time. The goal of the today video, which is called time dilation, is also a theory of Albert Einstein. So if we want to talk about this time dilation theory, we have to understand the behavior of the light very precisely. At the age of great philosopher Aristotle, there was an argument in the world which said that the speed of the light is zero. It means the light is not having any speed. That is null speed. But in the same era, there was another set of scientists who told that no, the speed of the light is not zero, but that is infinite. It means we can't measure the speed of the light. Now there are two parties and there are two contradictory ideas. One are telling that speed of the light is zero, and other people are telling that speed of the light is infinite. It has created a huge conflict among the research community, scientific community, as well as the philosophers. Anyhow, we can't see any significant experiment which was prepared to measure the speed of the light until the age of Galileo Galilei. This Italian astronomer as well as a physicist has done a remarkable experiment in order to measure the speed of the light. This experiment is called Galileo's lantern experiment. Here, he and his assistant went to two mountain crests with a lantern and a stopwatch in their hands. So what they have done? Galileo opened the closing lid of the lantern and marked the time of the watch, and his assistant, who is on top of a faraway mountain, notes the time which he sees the light. Galileo's intention was to measure the speed of the light with respect to that difference of the time, but he was not successful. So for a very little moment, we will keep this topic light aside and we will bring the topic which is called sound into our arena. What is the speed of the sound? You know the answer. The speed of sound is 343 meters per second. So what can you say about the speed of the light and the speed of the sound? What is the greatest one? So we will turn into an example. When thunder with lightning, you can have the sound of the thunder after seeing the light of lightning. So what is the greatest? Now you can understand the speed of the light is greater than the speed of the sound. So we'll go to the previous discussion again. A few moments ago, I told that Galileo Galilei was not able to measure the speed of the time. But on 1676, an astronomer called Ole Romer calculates the speed of the light with the aid of his friend Christian Huygens, who was also an astronomer. They have get the speed of the light as 222 million meters per second, and that was a very huge value, and it was the very first calculation of the speed of light. After this, many scientists calculated the speed of the light using various methods, and they came through various values for the speed of the light. Anyhow, on 1983, the speed of the light get exactly measured, and the value was 299,792,458 meters per second. This value was published during the 17th Conference of Weight and Measurement in 1983. So now we are having a very good idea about the light as well as the speed. So we can go into our main topic, time dilation. Think about this. In every second we age, but is that aging speed, is that aging frequency constant for each and every human being in the universe? Is your aging speed similar to the aging speed of the astronaut who is traveling in the rocket for a long time with a huge speed? Is your aging speed similar to a person who is in the moon? Is your aging speed similar to the scientists who are working on the International Space Station? Is your aging speed similar to a sailor who is traveling on board a ship? Now, assume that one person is traveling with 1/4 of the speed of the light. Then what can you say about his aging speed and your aging speed? Are those values different or similar? Isn't that question a brainstorming and a mind-blowing argument? To solve this question, we have to seek the solace of Albert Einstein's special theory of relativity. Prior to jump into the special theory of relativity, we have to touch the general theory of relativity smoothly. The basic rule of classical relativity, also known as the general theory of relativity, is no object is having absolute movement or immobility. It means we have to describe any motion of any object relative to another object always. Didn't you get the idea? Now you think that you are in a space and you can't see any object around you, and you are having a jetpack in your back and you start moving. Can you feel that you are moving? No, you can't feel. What is the reason? There's no any object around you to feel that you are having a relative movement. If you are not having a relative movement, you can't feel that you are moving. That is why general theory of relativity says that no object is having absolute movement or immobility. It means every movement must be relative. So when we are talking about this general theory of relativity, also known as a classical relativity, we come across two words. They are called distance and the displacement. Out of these two roots, what is the distance and what is the displacement? You know, the displacement is the shortest distance between two entities. That is the simplest explanation we can give to the displacement. Using these two terms, we can define the things called speed and the velocity. Speed is a value come from the division between distance and the time. That is the rate of change of distance. And the velocity is a division between displacement and the time, and that is the rate of change of the displacement. Anyhow, the unit of the both is meter per second. So, if we draw a graph for constant velocity or constant speed, that would be like this in a distance time or displacement time graph. And it would be like this in a velocity time or speed time graph. You can clearly see the difference of them. Okay. Now what can you say about the relative motion? So we'll go to the animation again. You can see there's a train and it is traveling with a constant velocity of 200 km per hour. And also there is a boy on the train and he is throwing a ball with the speed of 10 km per hour, and that is a constant speed to the direction of train's motion. On the other hand, we have an external observer also. Now what is the velocity of the boy inside the train? Since he is inside the train, he is getting the velocity of the train, that is 200 km per hour. So what is the velocity of the ball relative to the boy? That is 10 km per hour. But what is the velocity of the ball relative to the non-moving external observer? That is 210 km per hour. How can it be? Here, the observer gets the velocity of 210 as a resultant of the sum of the real velocity of the ball and the velocity of the train. Now assume that the observer is traveling with the velocity of 100 km per hour to the direction of the train. Now what is the velocity of the ball relative to the observer? That is 210 minus 100, that is 110 km per hour. So now you are having an idea about the relative motion also. Okay, now we shall go to the next level. Think that the boy in the train is having a torch in his hand and he turns it on and the light ray emits. Now what is the speed of the light beam relative to the external observer? Is that the normal speed of the light plus 200 km per hour. Here also the speed or the velocity of the light does not change. That remains constant and it does not depend on the observer. Now in our animation, the speed of the light relative to the observer C 299,792,458 meter per second. Now I have told you before, the speed of the light remains constant. Then what about the time dilation? Yes, I'm going to prove it using simple mathematics. So we'll jump into the animation again. Here you can see there's a boy inside the train with a constant velocity v, and he's having a torch in his hand. And also you can see an external observer. These two persons are having two atomic watches. Those atomic watches can be used to measure micro level time measurements. Here you can see the gap between the top of boy's torch and the train soffit is d. Now boy emits a light ray from the torch, and the time taken for that light beam to travel the d distance gets calculated in atomic watch as t. Using that values, can't you calculate the speed of the light relative to the boy? Let's represent the speed of the light with the letter of c. Actually, this letter c stands for the salinity. Previously, I told that the speed of the light is not relative to the any body. But since we are trying to prove the time dilation equation, I will say these phenomena relative to the boy and relative to the observer like that. Don't get messed up. So the speed of the light relative to the boy, which is c subscript a, is d divided by t. After this c subscript a will be uttered ca by me. Now the boy sees the path of the light beam as a vertical line, but what is that path for the observer see? The observer notes the direction of the light beam like this path. Now what happens? How can we calculate the speed of the light relative to the observer now? For that, we have to consider this triangle. You know that the vertical leg of the triangle is d and the horizontal leg is vt. Here, v is the velocity of the train and the t is the corresponding time. Then the length of the diagonal can be calculated using the Pythagoras theorem, and it is like this. Okay, now can't we express the speed of the light relative to the boy and the observer separately? Here, speed of the light relative to the boy is d divided by t, and the speed of the light relative to the observer is full square root of d squared plus vt squared divided by t, and these values are not equal. Now what has happened? This situation does not tally with the rule says that the speed of the light does not vary with respect to the observers. According to our calculation, speed of the light relative to the A is lesser than the speed of the light relative to the C, and that is utterly wrong. Now how can we solve this conflict? In our equations, V and the D can't get changed. So the one and only variable is t, that is time. Here we know Ca is equal to d divided by t, and Cc is equal to the full square root of d squared plus vt squared divided by t. To become Ca equals Cc, full square root of d squared plus vt squared value must be divided by a bigger time value than that of Ca. In other terms, the rate of the time of the C's whirl is greater than the rate of the time of A's whirl. That is the beauty of this argument. Simply, the aging speed of the boy A is slower than the aging speed of the observer C. Don't get confused. I'm going to prove it using the animation again. Now we will take the time indication of C's watch as delta t and the time indication of A's watch as delta t naught. If it is so, vertical leg of the triangle is C delta t naught and the horizontal leg is V delta t. The remaining is the diagonal, and that is C delta t. If we use the Pythagoras theorem, we can write it as C delta t squared equal to V delta t squared plus C delta t naught squared. We can simplify the equation further and get a value for delta t naught squared. At last, I can write the equation for delta t also, and it is like this. Here the only variable is the velocity v. The most important thing is we can use this equation only for the objects moving with a constant speed. It means if the object is moving with the acceleration or anything else, we can't use this time dilation equation. Actually, this time dilation equation was a new chapter of science as well as physics and mathematics. So don't you like to solve an example with me? Okay, come with me. Here delta t naught is 10 seconds and the velocity is 85% of the speed of light, and it can be represented at 0.85 c. You know, c is the indication of light which came from the salinity. Then the equation will be like this. Finally, we get delta t as 18.98 seconds. What has happened? The time of A's world is 10 seconds and the time of C's world is 18.98 seconds. Here, when A's clock indicate 10 seconds, C's clock indicate 18.98 seconds. If we think this with respect to the aging, C ages 8.98 seconds greater than A. Okay, don't you like to have another example? Come with me again. Here, A travels in the space with 95% speed of the light during 10 years on board the spacecraft. And here, delta t naught is 10 years and we will substitute the values to our time dilation equation. The answer for delta t is 32 years. The conclusion is A has gone old slower than C. Can you see the beauty of this phenomena? The traveler A travels in the speed with 95% speed of the light in space during 10 years. So he ages only by 10 years. But his friend in the earth ages 32 years in the same time gap. This is the time dilation. Now think that we are traveling with the speed of the light. What will happen now? According to the time dilation equation, our aging must stop. It means we don't get age if we are traveling with the speed of the light. So what will happen? Any traveler exceed the speed of the light. If it happens, he will age backward and each and every laws of the physics will turn upside down. Because of that, there's a law in the physics that says any moving object can't exceed the speed of the light. So this is the time dilation equation, but this is a very tiny piece which shows the beauty of Einstein's special relativity. And also this is how we can age slowly with respect to the time dilation as well as special relativity. This is not only an empirical equation, this is an actual phenomena. It has been proven using atomic clocks on airplane experiment, GPS satellite experiment, Michelson and Morley experiment, moon particle experiment, and so on. If you want to study this time dilation deeply in a research level, you can find a number of journal articles, research papers, review papers, and book chapters in reputed journal databases. I am also having a good collection of research papers regarding the time dilation, classical relativity, as well as special theory of relativity. If you want those papers, you can request it through my Telegram group, ThinkX community. So this is the end of today's discussion. If you want to talk about this type of topics with me, you can connect with my Telegram group, ThinkX community. So if you got any knowledge from this video, I invite all of you to share my video, share my YouTube channel in the Facebook, in Instagram, in WhatsApp, or in any sort of social media, as well as among your friends. So keep in touch. I will meet you with another video as soon as possible. I am Madhujit Sagar.